Hi, I'm Amin Shiraz Gilani, and today we will talk about quantum advantage and lower bounds in parallel query complexity. This is joint work with Joe Carolyn and Mahati Vempati, who are fellow students at the University of Maryland. So let us begin with the definitions of query complexity. This is the model we'll be interested in. The query complexity of a Boolean function with respect to a model is the minimum number of queries made to the respective oracle to compute it on a worst case input. So a classical oracle will take an index and output a corresponding bit, whereas superposition queries could be made to a quantum oracle. We will consider three natural models of query complexity. In the deterministic model, the oracle is classical. There is no access to random bits, and the correct answer should be output with certainty. While in the randomized model, the oracle is still classical, but there's access to random bits, and the desired success probability is a constant greater than 1/2. The quantum model is a quantum oracle analog of the randomized model. It is easy to see that the quantum query complexity is at most the randomized query complexity, which is at most the deterministic query complexity for all functions. Now let us generalize these definitions to allow for parallel queries. Similarly, the p-parallel query complexity of a Boolean function is the minimum number of p-parallel queries made to compute it on a worst-case input. So a p-parallel classical oracle will take p indices as input and output p corresponding bits, whereas again superposition queries could be made to a quantum oracle. Similarly, the models of parallel query complexity could be defined with respect to p-parallel oracles. Again, it is easy to see that for all functions f, the quantum p-parallel query complexity is at most its randomized analog, which is at most its deterministic analog. Note that one parallel query complexity is the same as the sequential query complexity that we defined earlier. There are some easy to see bounds in the p-parallel query complexity. So the first inequality here follows since p sequential queries could simulate one p-parallel query, while the second inequality follows since one p-parallel query could simulate one sequential query. Let us now see the known relationships between deterministic, randomized, and quantum query complexities for total functions. From the work of Beals et al. And Ernst et al., we know that for total functions, the deterministic query complexity is at most the fourth power of the quantum query complexity. On the other hand, some of the relatively recent work exhibited functions that demonstrated superquadratic quantum advantage for total functions. In particular, the result of Ernst et al. Introduced the notion of cheat sheets, which will be very useful in our constructions. Jeffrey et al. Did a systematic study of parallel query complexity and conjectured that the deterministic parallel query complexity is polynomially related to the quantum parallel query complexity for all total functions and all choices of parallelism. In fact, they showed this conjecture is true for all total functions in parallelism polynomially smaller than the block sensitivity. But is this conjecture also true for P at least as large as the block sensitivity for all total F? Let's hold on to this question and we will get back to it. We begin describing our results by first outlining them and then talking about each of them separately. First, we show an unbounded parallel quantum advantage for total functions, refuting the conjecture of Jeffrey et al. That we just discussed. Then we define a notion of genuine parallel quantum advantage and show that there is a total function that achieves it. Then we describe an alternative measure relevant to parallelism and construct a function that attains a quantum advantage with respect to this measure. Lastly, we talk about a new lower bound technique for parallel quantum query complexity. Our separations in items 1 to 3 are between quantum and randomized parallel query complexities, but we note that our constructions can be modified to show analogous separations between randomized and deterministic parallel query complexities. So let us start with our first result. We begin by intuitively describing the cheat sheet function we mentioned earlier. The cheat sheet framework takes a partial function f with an exponential quantum advantage, such as the correlation function, and lifts it to a total function, which we call FCS, that retains some of its speed up. So an input to FCS comprises of two components, an address component and a data component. The address component consists of inputs to logarithmically many instances of f, composed with g, where g is a total function with small certificate complexity, such as the NDOR function. Computing the output of these instances gives a logarithmically sized bit string, which can be used to specify the address of a location in the data component. We say that FCS outputs 1 if and only if the contents of this location in the data component contains a certificate for all instances of G. Let us now look at an intuitive quantum parallel algorithm for FCS. Let P be the parallelism which is at least as large as the input length of G, and the product of the input length of F and the certificate size of G, yet is polynomially smaller than the randomized query complexity of FCS. You may believe that there is such a parallelism. Since F is quantumly easy and P is large enough, we can compute the output of all instances of F composed with G in one P parallel query. Moreover, it is sufficient for the size of each data register to be at most P, as it is easy to certify G and P is large enough. Thus it can be read out in one P parallel query as well. It follows that querying the indices given by the information read out earlier is sufficient to verify if it contains a certificate for all instances of G, which we can also do in one P parallel query. Therefore, three P parallel quantum queries suffice to compute FCS for this choice of parallelism. We know that the randomized P parallel query complexity of FCS is at least the randomized query complexity of FCS over P. Thus, a polynomial lower bound for the formal can be established by using the fact that P is polynomially smaller than the randomized complexity of FCS. We also show that the block sensitivity of FCS is not too smaller than P, refuting the conjecture of Jeffrey et al. In the strongest possible way. Now we talk about our second result. Before we describe our result, we discuss what we mean by genuine here. We saw earlier that a super quadratic sequential quantum advantage due to the cheat sheet function can be amplified to an unbounded parallel quantum advantage. But is such a sequential quantum advantage necessary? In other words, can there be an unbounded parallel quantum advantage without there being a sequential advantage? We answered this in the affirmative. We begin with the definition of correlated output functions, which you would have already guessed by its name. We use core as a short form for correlated output functions. The core of F1 and F2 takes two inputs, one for F1 and one for F2. These inputs satisfy the promise that the outputs on F1 and F2 are the same, and the goal is to produce this output. Intuitively, if you want to solve core of F1 and F2, you would need to solve one of F1 or F2. We make this formal by showing that for deterministic parallel, randomized parallel, and quantum query complexities, this is the case. Now we can talk about the construction of our desired partial function, f partial. Let f1 be the pointer choosing function with pointer length m, which is much smaller than the input length. Let f2 be the composition of parity on m bits with correlation on m squared bits. We define f partial to be the core of f1 and f2. We make a few observations about the complexities of f1 and f2. Firstly, the randomized and quantum sequential complexities of f1 are theta of m. Since m is much smaller than the input length, so the best thing you could do is follow the pointers. Secondly, the randomized parallel query complexity of f1 is at least m for small enough parallelism, again for the same reason. Next, the quantum query complexity of f2 is at least m, since you need to compute m parities, and it is quantumly hard to do that. Finally, for some small enough parallelism, the quantum parallel query complexity of f2 is 1, since f2 can be perfectly parallelized. Moreover, at this parallelism, the randomized parallel query complexity of f2 is still at least m, since the randomized sequential query complexity of f2 is m squared. Now we look at sequential and parallel bounds for f partial. We noted that a randomized sequential algorithm could solve f1 in O of m queries, so the randomized query complexity of f partial is O of m. We also noted that a quantum sequential algorithm would not benefit from solving either f1 or f2, so the quantum query complexity of f partial is omega of m. For some p in theta of m, we saw that there is a quantum p-parallel algorithm that could just solve f2 in one query, so the quantum p-parallel query complexity of f partial is just 1. On the other hand, for all p in theta of m, any randomized p-parallel algorithm would not benefit from solving f1 or f2. So the randomized p-parallel query complexity of f partial is omega of m. In summary, the sequential quantum and randomized query complexities are almost the same. Yet for some choice of p, the p-parallel quantum query complexity is much, much smaller than the p-parallel randomized query complexity. We briefly discussed how we would totalize f partial to attain a function f total using the cheat sheet framework, but here we would need to make some modifications. Firstly, if we were to choose the function g to be the end-or function, then since the quantum query complexity of end-or is much smaller than its randomized analog, it would help the quantum algorithm solve f total faster. Um, so this wouldn't work. So we actually want a function that does not admit a quantum advantage, but still has small certificate complexity. Fortunately, Aronson et al. Constructed such a function, which we use. Secondly, we want to have the quantum and randomized sequential query complexities of f total to be around the same. So showing a lower bound on the randomized sequential complexity of f total is not sufficient here to get a good lower bound on its parallel analog. Thus, we show a randomized parallel composition theorem to get the desired parallel lower bound. Next, we move on to our third result, which is what we call quantum advantage with 2 rounds of adaptivity. We begin with some context for this result. An alternative complexity measure relevant to parallelism is the amount of parallelism needed to compute some function for a fixed number of adaptive rounds. More precisely, we define the k-adaptive query complexity of a total function as the minimum parallelism, such that for this parallelism, the p-parallel query complexity of f is at most k. As before, we use some notation to denote the k-adaptive, deterministic, randomized, and quantum query complexities. One result of Montanaro says that the non-adaptive quantum query complexity of a total function is related to its deterministic analog by a constant factor. We saw earlier that the cheat sheet function achieves a polynomial separation between three adaptive quantum and randomized query complexities. Um, so a natural question to ask is what is the picture for two adaptive query complexity? In particular, can there be a polynomial separation between two adaptive quantum and randomized query complexities? We give an affirmative answer to this question as well. We now describe the construction for the desired total function, which we call F2 adaptive. We take a partial function that exhibits at least a polynomial separation between non-adaptive quantum and randomized query complexities, such as the correlation function, to construct F2 adaptive that exhibits the desired polynomial separation. Our strategy is to essentially break the data component in the cheat sheet framework into two registers, one of which is short and the other is long. We say that F2 adaptive is 1 if and only if the short register contains the certificate that validates the input to the address component and the bit in the long register addressed by the string specified by the output of the address component is 1. First, we look at the intuition for why this function can be computed quantumly using two adaptive rounds. So the first round, a quantum algorithm computes the output of the address component as well as reads the contents of the short register. Then in the second round, it verifies that the short register indeed contains the desired certificate, along with querying the bit at the right address in the long register. Then it simply outputs this bit if the certificate is valid, otherwise it outputs a 0. This step requires no queries. So we could compute this function in two adaptive rounds. Next, we look at the intuition for why a randomized algorithm cannot compute this function in two adaptive rounds. Since f is classically hard, any randomized algorithm cannot compute the output of the address component in the first round with high probability. This means that it can only query the bit at the right address in the long register with very small probability. However, there is a subtlety. It could be possible that the structure of a zero certificate might be easy to distinguish from the structure for one certificate, which might help a randomized algorithm compute the output of the address component in the first round, since the randomized algorithm can query the short register and get the certificate. To deal with this issue, we introduce the notion of bi-certificates, which are certificates that could certify both zero instances and one instances. So just looking at the certificate will not help a randomized algorithm compute the output of the address component. Let us move to our last result, where we'll talk about a new parallel quantum query lower bound framework and some of its applications. We begin with the discussion of a barrier for the parallel analog of the combinatorial adversary method using the example of the AND/OR function. Burnham and Sachs showed a lower bound on the sequential combinatorial adversary quantity for the AND/OR function to be the square root of n, which implies the corresponding lower bound on its quantum query complexity. Also, a result of Zalka states that the quantum parallel query complexity of both the AND and the OR function is the square root of n over p. Then what is a good guess for the quantum parallel query complexity of the AND/OR function? Is it square root of n over p? We show that the parallel combinatorial adversary method cannot show a lower bound better than the square root of the product of the zero certificate complexity over p and the one certificate complexity over p. In particular, the parallel combinatorial adversary method cannot show a lower bound better than the square root of n over p. Better than the square root of n over p for the AND/OR function. But is this the best possible lower bound? We'll get back to this question. Now we describe our parallel quantum lower bound method. We begin with a couple of definitions. For any total Boolean function f, let calligraphic f sub p denote the set of all functions obtained from restricting f to p input bits and fixing the rest. Let adv1 of f be the adversary quantity of f, but with the optimization restricted over matrices that have non-zero entries only on input pairs indexed by xy, with f of x not equal to f of y, and um, x and the Hamming distance between x and y being exactly 1. Then we show a lower bound on the quantum parallel query complexity of f in terms of adv1 um, of f and adv1 of g, for g being the restrictions of f to p input bits. Noticing that adv1 of g is at most the quantum query complexity of g, we get a lower bound in terms of quantum query complexity of restrictions of f to p input bits. Uh, Therefore, we have reduced the problem of lower bounding the quantum parallel query complexity of a function to upper bounding the sequential query complexity of its restrictions, which is usually easier to analyze. Finally, we describe some applications of this lower bound. Uh, First, for any symmetric Boolean function f, we have the quantum p parallel query complexity of f lower bounded by the square root of nt over p times the minimum of t and p, where t is the Hamming weight closest to n over 2, such that f differs on inputs of Hamming weight t and t plus 1. Thus, we recover the result of Grover and Radhakrishnan using an arguably simpler proof. Secondly, we show that for any Reed-Once formula, its quantum query complexity is lower bounded by square root of n over p. In particular, we have surpassed the barrier we mentioned earlier for the AND OR function to get a tight lower bound. Finally, we talk about some open questions relevant to our work. Firstly, what are the limitations of parallel quantum speedup? For all total functions, can a deterministic algorithm simulate a p-parallel quantum algorithm with a polynomial overhead in parallelism and in the number of queries? Secondly, can we show a quantum parallel composition theorem? In particular, is the parallel query complexity of f composed with g equal to the product of the parallel query complexities of f and g with an optimal distribution of parallelism? Lastly, are there any natural functions that exhibit the quantum advantages that we saw? Um, Thank you for listening to my talk, and here are the papers I referred to during this talk. Thanks again.